Okay, so in order to start this problem, we have to draw a free body diagram. All force problems we have to draw a free body diagram. So I've set up the incline, and I've drawn my box, which represents the flume ride, and I've drawn towards the center of the earth the force of gravity. The normal force lays perpendicular to the surface that the object is resting on. The force of friction opposes the direction of motion always. Then I'm going to break my vectors up, my force of gravity, into its components, Fgy and Fgx. From here, I'll be able to solve for all of my forces here. So the first one is Fgx. Since Fgx is opposite of the angle, we can use the sine function. So rearranging this to solve for Fgx, we get Fg sine theta. We can break Fg up and make it more compact by saying that Fg is equal to mg. So now Fgx is equal to mg sine theta. Now, according to the hint, we're going to leave it like this until the end of the problem. Now we can do the same thing with Fgy. Fgy is the adjacent side to the angle, so we're going to use cosine. Rearranging the problem, solving for Fgy, we end up getting Fg cosine theta. Again, we're going to say that Fg is equal to mg, so that our final product here is Fgy is mass times the acceleration due to gravity times the cosine of theta. Next, we're going to take a look at the sum of the forces in the x direction. And remember, we tipped our axis so that it runs along the plane of the inclined plane. So now the sum of the forces is equal to the force of friction, which we said was mu times the normal force, plus Fgx, replacing Fgx with what we solved for earlier, mg sine theta. Now we don't know what Fn is, so that's our next step. What we do know is that the sum of the forces in the y direction is going to be equal to 0 because it's not accelerating and it's in equilibrium in the y-axis. So we have the normal force plus the Fgy. Solving for Fn now, we get Fn equals negative Fgy. Substituting in for what we already know, Fn is now equal to negative mg cosine theta. Now here I've asked the question to kind of get you to think about how to solve for A net. So the second law is saying that the sum of the forces is equal to mass times the net acceleration. We already know that the only direction that it's accelerating in is the x, so we're going to use the sum of the forces in the x direction in this case, which we have solved for above. This equals our ma net, and this will be a net acceleration in the x direction. Now we know Fn, because we solved for that above, so we can plug that in into the new formula. So now we have mu, the coefficient of friction, times mass, and acceleration due to gravity, cosine theta, plus mg sine theta, which was, again, our sum of the forces, or comes from Fgx. Now look at this. All of our masses cancel out. We have two masses on one side, and we have mass in each term, so they can cancel each other out. This is why I wanted you to save the formula, make it in formula form until the end of the problem. Okay, rewriting this, we give mu g cosine theta plus g sine theta equals our net acceleration. So I'm just going to rewrite this again in terms of A net. And if you notice here, I did make a little mistake. I'm going to fix that mistake by adding a negative in front of the g cosine theta. This is because I forgot to write it when I substituted in for Fn. So rewriting it again, we have A net equals negative 0.12, which is our coefficient of friction, times the acceleration due to gravity, which is also negative, going towards the center of the Earth, the cosine of our 43-degree angle, plus, again, a negative 9.81 meters per second squared, acceleration, times sine of 43 degrees. So plugging all of this into a calculator, or each part into a calculator, we get 0.86095 meters per second squared. Okay, remember, two negatives make a positive. That's why this part is positive. This one ends up being a negative 6.6904 meters per second squared. Now both of these have the proper units for an acceleration, so we can proceed with the rest of the problem. We end up getting 5.82945 meters per second squared, and putting that so that it has proper sig figs, we're going to change that to negative 5.8 meters per second squared. So, in the end, we have an acceleration that follows the slope of the inclined plane down the inclined plane. So the last question we have to ask is, does this answer make sense? Which it does. We know that it's going down the plane, so it should have a negative net acceleration. It has the units for acceleration, so this problem looks good.